Well, in this lecture, I want to talk about keep this structure, a latent shift reduce parser for semantic parsing, which is this great article by people in Microsoft. So it's a shift reduce parser, and so it's not a graph-based algorithm, it's a transition-based algorithm, and we use it for semantic parsing. So the basic idea is like any other shift reduce parsing, you have an input buffer, we have a stack, so we have an initial configuration. A shift reduce parsing is not only efficient, but also our brains uses that, and cognitive science has explained it. And it captures short-range dependencies. It is faster than arc-factored models, and it is bad for long-distance dependencies, such as verbs. So we have three actions, shift, left, and right. And features, you can use the top of the stack, you can use the top two words in the buffer, and the part of speech of words. So we can build the three-way classifier shift, left, and right. And so, for example, an example from this article, what is the area of the country? And so you can, this natural language hierarchical structure has a logical form hierarchical structure. So for any natural language query, there is a logical form. So the idea of this paper is that it has two parts. First, the parser, which is the base model for use for parser is just a simple let's say a simple sequence to sequence model. You can use it for the base parser, but the base parser only produces these parts for just some a span that is separated by the splitter algorithm that I will explain. So given a natural language query, it first uses shift reduce splitter to read tokens by shift operations and detect the hierarchical structure. Once a semantic span is detected, it takes a reduce operation to convert it to a sub-logical form with a base parser. Your base parser could be anything. And then uses span semantic vector to replace the original span. This process goes iteratively until the whole natural language query is parsed. For example, what country the case, so this is a span. So the splitter understands that it should split from here so that it's just a vector. So instead of something, a vector is a good representation of some splitted, sequence of words that is splitted from the original sentence, so that we can just split it. It's very nice because you can do recursively, so it's like dynamic programming. You can do it very recursively, but you will see that we implement this using stack LSTM, which I have explained stack LSTM in a different lecture, which is very nice. And so this is another example. For example, when we say what is the most popular state through what the Mississippi goes. So the trajectory is like this. First you do shift, and then you reduce, but you reduce it, you separate the last 6 tokens, then you reduce it, but you separate from the last 4 tokens, and then you reduce it, but you consider the last 3 tokens. So you see that this is the base parser. Each of them has a base parser. So each one is just a simple sequence to sequence. Natural language to the logical form. But the important thing is the first module, which is the separator, splitter, that separates some of the words, a sequence of words from the rest of the words in the sequence, and do it recursively, like this. So the contributions is, it is a late shift reduce parsing module. The base parser, so it has the base parser and the splitter, two modules, the base parser and splitter. As I said, the base parser could be any usual sequence to sequence. I mean, just translate a sequence, a natural language, to a logical form. But the important idea of this is to combine it with splitter, because if you split each of them, if you split it, for example, this span we can understand the logical form of it very quickly. And for any span, these translation idea of the semantic parsing, which is the easiest one, could be used. But the important thing is to how can we split these sentences into some spans and do it recursively. So because all of this is just a vector goes here, and so it's just a nested thing, just like any other idea. So we have first we have this vector that I said. We need a vector, a span semantic vector. For example, we should represent this by vector, and we use ByGRU as an encoder of U. U is just the embedding of your your sentence, the sentence that you want to embed. For example, you want to embed country in KC time zone, just this part. So this is V, and once you know V, you can create, you can generate the logical form just like sequence to sequence. So this is the encoder of the sequence, and this is the decoder of this sequence to sequence model. So you know everything that if we could do this span, if we could do the splitting, then everything is standard and very easy. So there is no issue. But the idea is this shift reduce splitter. You know, shift pops the first token from the buffer, pushes it into stack like any other shift reduce algorithm. I mean, transition-based algorithm. And then you have reduce K, but this is non-standard because in reduce, you usually say reduce K is 2. We pop out usually the last two tokens from the top of this stack. But here it generalizes that, so it's just it pops K tokens. And then we have another thing, another action, which is finish. FIN is a shortcut to reduce, which pops out all elements from the stack and finishes the shift reduce. So this is the idea. It uses a stack GRU. I've explained this stack GRU in a different lecture. This is a very beautiful architecture. It has improved natural language processing, just like tree-LSTM, which is another beautiful variant of LSTM. So this is a stack GRU. You can have the stack LSTM with the same analogy. So first we create meaning representation. I mean, for a sequence of words, we can have a sequence of part of speech. But here, part of speech, we don't care about part of speech. Here, we care about semantic tags. So if the length of your sentence is M, then the semantic tags has M token, has M tags, let's say. You can use it with CRF LSTM, as I've done it in my paper, but you can. But here it has just used ByGRU, which is very easy, and we can do it very quickly. And so you say that how do you represent your stack? So we say I represent it by word and then concatenate it with that semantic tag, and then the last the last stack element. So for next time, you have a different time, different word, different time, different word, and different time until the end. But here, for example, uses reduce 3. It means reduce the last 3 elements in your stack. So we are representing it based on the actions. For example, if the action is shift, we use this. So it just needs the last element as well as one of the tags that you need, one of the tokens that you need. But if it is reduced, you use v. V is that vector that I said that you split some part of that, and this some part could be represented by v. And as if you remember, v is just the v has this simple formula that says v is here by GRU of u. So this is v, as I said, country, the KC time zone, county in the KC time zone. And so v is represented by this vector because we need this vector to go to the larger span. So if you come back here, so now that we have this stack, now that we know the last stack element, we know the embedding of the semantic tag, or even word representation, the word embedding. And also E prime is the element from the buffer. Like any other transition-based algorithm, we also need a feature from the buffer. So this is from the buffer. Now, if you concatenate these 3 elements, you get z of t at time t, and you just use a multi-layer perceptron and take the maximum and in order to get the action you need. And then, so now that you know the action, if it is shift or it is reduce, you need to know reduce how many times. As I said, it's a generalization of reduce because the standard one is reduce 2 and k is 2. But here we generalize. Instead of 2, we have k. K could be anything, but it is fixed. So it is fixed. So we use this technique that we say because it's just either 2, 3, or k. So we use this dot product of z of t, which is this embedding with these r in order to create to know the p. And once we know the p, that's it. We know how we have reduced, so we know the action. But now we know what is the probability that, for example, k is 3. For example, like here, what is the probability that the last 3 tokens are enough to be separated? And the training is very easy. We design a trajectory search. And the important thing which is challenging here is that because we don't have, in the training data, we don't have these trajectory of shift, reduce, and it is tedious and it is not in harmony with what our brain does. Our brains never remembers the sequence of shift or reduce or those things. But what our brain remembers is that this logical form, that we can create a logical form inside our brains. So that's why this is used. So how can we relate that with this? We say, I always say it's kind of distant supervision, because you are not taking this as a supervision, you are not using this. So this is your latent variable. So if you use expectation maximization algorithm, so I've explained expectation maximization algorithm in natural language processing playlist, so you can watch that. So once again, we are using expectation maximization. So you know that this one is 1 because this is we are marginalizing over all action sequences. So each of these A is just a sequence of actions: shift, reduce, shift, reduce. and so on. So we are marginalizing. We know that all of them should have, should create the logical form that we want, the gold one. So it's simplified to this. But how do you use this? So we use this ranking, heuristic ranking, that says, okay, we just need to have some some classification saying, for example, this is correct, this is partially correct, a fuzzy things, a fuzzy classification. And we are so this article in Microsoft, it has written just this paragraph for this whole beautiful idea, but it is much more complicated than this, than just one paragraph. They could have written more paragraphs about it, but because it is beautiful, and they could share their this beautiful representation. But you know that here, because we have the training data, we can say like. Because, for example, this idea is like a pattern. You see it in all articles. You see that, for example, when you don't have such thing, you put it as a latent variable, but you adjust it because some of these, some of these trajectories are infeasible. They are not feasible. So how do you adjust it? As I said, by expectation maximization algorithm. So this is just a latent variable. You use the error, your loss, to find the parameter theta, and parameter theta, you find the latent variable, which is z here. Z, for example, this trajectory A is here. So latent variable, let's call it A. And so it's just expectation maximization. You expect something. This is the latent variable expectation. You maximize something with respect to theta. This is the parameter that should be learned. So I said everything, all the beautiful ideas. And you can use pre-training as well. This is standard. You do it in all articles. So this is an example. You have a splitting, and some of these splitting are correct. Oh, by the way, somebody can write a paper about this and say, for example, because we are, you can use the idea of human-computer interaction. Human-centered. Let's say they call it human-centered AI, artificial intelligence. So the machine can tell you that if something is correct and or not, and the crowdsourcer says, oh yes, this is correct. So the machine asks, can I do this? So if we are teaching, it is learning how to teach. So this is really important, because here somebody can write a paper about this and implement the human-computer interaction. Human-centered semantic parsing. I think there are written many papers, but in different directions. But in this framework, somebody can just understand how we can use the human-centered AI. So the machine asks what kind of question is correct, or what is the answer to some of the questions of the machine. So we are not labeling. We are not labeling as humans. We are not labeling it, but the machine is asking us their questions and understand what to label. The machine understands what sentence should be labeled, or what problem should be labeled. And so the accuracy of this algorithm is quite interesting. So they use the splitter, and so they have high accuracy for GeoQuery. Of course, GeoQuery is relatively very simple in comparison to, for example, complex web questions. So that's why here it has less accuracy. It has 68% accuracy in comparison to 85%. And there are other articles as well from very great people. And this article is also interesting, and that's it.